Thanks, Jacob. So it is a great pleasure, I'm sure I can say on behalf of all the Indian participants, to be here and in this beautiful city once again. I think this is my 4th visit to Rio, and I must say every time it looks as beautiful, if not more beautiful than the last time. So let me begin. So on trace formulae, and this was something which has been done in collaboration with my student, Arup. This is a little small handwritten prelude. So let me give you a very simple background to the problem or this genre of problems. So consider, is this on? Consider two n by n complex symmetric matrices A and B and form that combination with a real parameter S in the interval 0, 1. So it is a family of symmetric matrices, and then look at the eigenvalue sequences for each S. And look at that, the family of eigenvalues as a function of S. How does it move? It is known, it can be proven easily because it is a solution of an algebraic equation. It is a piecewise differentiable function of eigenvalues of AS. But if we look at it as an analytic function, then of course algebraic singularities can occur. Now if we do this simple calculation, you just take this eigenvalue equation and differentiate it, and then you can compute this formula which I have written in the next line, compute the trace of the perturbation B with the spectral measure for the interval delta and for the matrix AS for S in this interval, and call that ES of delta. Take the trace, that is, can easily see is this, and then if you integrate that, so this is not an absolutely continuous function. It has jumps. It is just collection of jumps over an interval. So, but if you integrate over the parameter space, those jumps disappear. It becomes an absolutely continuous function with respect to the Lebesgue measure. So this simple statement appears a little mysterious, and this is of course in finite dimension that I have made this statement, but this statement remains true in infinite dimensional Hilbert space as well. And that is the content of what is known as Crane's theorem, that this integral is absolutely continuous with respect to Lebesgue measure, and the Radon-Nikodym derivative is called the Crane's shift function, and you have this formula that Crane derived, which is called the Crane's trace formula, and you have function of A plus B minus function of A. Take the trace, and this is related to the integral of the derivative of the function with respect to this Crane shift function. So this you can look at it in many ways. One of the ways is what I have described in finite dimension. Other is kind of a mean valued theorem of operator functions. So it is the second attitude that I am going to take for, so the most part of my talk will be the asking the natural question that this is Crane's formula, that is if you form function of A plus B and subtract from the function of A and take the trace of the difference, it is given in terms of the first derivative of the function with a certain other function called the Crane shift function. This is, by the way, is an L1 function. Now, what happens if I go to the next order? In mean value theorem, you would ask next, if you think of this as a first order mean value statement, the next order will be if you subtract from it some kind of a derivative of the function evaluated as an operator, then what will be the right hand side? So that is the question, and that is what I try to answer. Okay, so this repeats what I just now essentially said. The first part is that, so this is a statement of Crane's theorem, that let H and H0 be two self-adjoint operators in a separable Hilbert space such that their difference is traceable in the Hilbert space. Then Crane proved that exists a unique real-valued L1 function Z with support in the interval, which is essentially the union of the spectra of H and H0, such that trace of the function of the unperturbed operator minus the trace of the function of perturbed operator minus the function of unperturbed operator. This is firstly trace class, and not only that, trace of that is given, as I had said, for matrices phi prime multiplied by a certain L1 function, which is called the Crane's spectral shift function. And this is called the Crane's formula. The original proof of Crane uses analytic function theory. I think the original proof was given in the late 1950s by Crane. But in 85, Voiculescu approached this formula in another way, another spirit, namely, he showed for bounded self-adjoint operators, if you take polynomials, these functions are now polynomials, and you form the functions of H and function of H0, take the difference and take the trace, then it can be shown easily that it is a limit of traces of finite dimensional compressions of these self-adjoint operators. Now these compressions have to be a little bit of special compression. So by adapting the Weil-von Neumann's theorem, Hn and H0n are some special compressions of the given self-adjoint operators. And we, that is Mahapatra and myself, extended this method to unbounded operator case and unitary operator case as well. And as I said, this can be thought of as a mean value theorem under trace for self-adjoint operators. Then a natural question arises, if you can have a similar theorem for the next order. Koplienko did provide such a formula, but unfortunately his proof was wrong. H and H0, so the statement is the following, be two self-adjoint operators such that the difference is now is not in trace class anymore, but B2 means Hilbert-Schmidt class. In that case, the difference of the two functions is no longer trace class, and one has to consider this, subtract from it this first derivative, where d phi is the Frechet derivative of phi at H0 acting on the operator V. For a definition, one can find many places. Find a trace formula for the above expression. And Koplienko's theorem asserts that there exists a unique function eta, which is in fact non-negative, L1, such that this difference is trace class and the trace is given by second derivative of the function as it probably intuitively should have been times the eta integrated. For Koplienko, he took these functions which are rational functions with poles away from the real line, but actually you can enlarge the class much more. The function eta is called Koplienko's spectral shift function. More recently, people have taken up this thing. Interest has been revived again, and Simon, along with his collaborators, gave an alternative proof for this formula for the bounded case. And in 2009, Dykema and Skripka, and earlier Boyadiev, proved the similar formula, but in different kind of context. Dykema is a specialist in free probability theory. So, and he brought to bear upon this problem the apparatus of inverse Cauchy transforms, and he derived this formula. Boyadiev obtained this formula in the context of a semi-finite von Neumann algebra setting, so more general trace situation rather than B of H. That's the only difference in Boyadiev's work and other people's work. Here we prove both formulas, both cases, bounded and unbounded, using the finite dimensional approximation philosophy of our earlier work. So this is the first theorem. This is a bounded case. This is the first part is in finite dimension. So first we prove a formula in finite dimension, then we find an appropriate approximation for infinite dimensional case and extend it, just as I said, for the Crane's formula. So these are collection of simple results, which is, this is the calculation of the Fresher derivative of a polynomial, operator polynomial. It's quite elementary, these calculations. And similarly, if I form HS is just as in the first slide, you interpolate between H and H naught, linear interpolation in this real parameter S, and you take the polynomial and differentiate. In a bounded case, these are all elementary computations, so these are just simple results. Then we prove the Koplienko formula for finite dimension. So these are for matrices. So you take the polynomial of H minus polynomial of H naught and subtract the first Fresher derivative acting on V. And you get the second derivative of the polynomial times this non-negative L1 function. So there exists a unique non-negative L1 function such that this formula is valid. Furthermore, some properties of eta, in fact in finite dimension, you can get an explicit expression for eta. Again, you see that the expression is related to this averaging over the perturbation interval S, 0 to 1. And these are the spectral family. This is for H naught, and this is for HS, for the perturbed one. And V is the perturbation. And the L1, this is non-negative, so the L1 integral of eta, or the integral of eta, is exactly equal to half the Hilbert-Schmidt norm of the perturbation square. So this result is true for finite dimension. What I will assert, next theorem will assert probably, or the theorem after that, is that this theorem remains true in infinite dimension except for this expression. This is no more valid. You can almost see that in finite dimension, trace is a trivial statement. Everything is traceable, but in infinite dimension, it is a non-trivial thing to prove. And this is not going to extend as a trace class object in infinite dimension. Well, I think I will not go through the proof. This is just some of the simple computations. So this is just the proof that the Fresher derivative is what I had claimed to be, and similarly the ordinary derivative, but this is the part which is a little instructive. So we are in finite dimension, so no worry about whether something is trace class or not. So we look at this polynomial, in fact simple power, h to the r, say minus h naught to the r, minus the Fresher derivative of h naught to the r acting on v, and take the trace thereof. And you can see this is the expression. The trick is to write this as an integral of derivative. Okay, so that's all we do. Essentially, it is a application of fundamental theorem of integral calculus at the operator function level, and you get this formula using the spectral representation of these self-adjoint operators, spectral theorem. And then what you do is you do an integration by parts. So, and that the boundary terms vanish. Oops. So here, you see, if I do integration by parts, this is in a bounded interval, I will get the difference of the spectral families at the two endpoints. Left endpoint, it is 0 by definition of spectral family. Right endpoint, they are both identity, therefore difference is 0 for this. So the boundary term vanishes, and what you get is this formula, where eta you read off is this expression, as I had written earlier. Uniqueness of eta follows from the uniqueness of a probability density supported on a finite interval with a given sequence of moments. To prove the positivity of eta, we use an idea of double spectral integrals, which was introduced by Birman and Solomiak. So we approximate the spectral measures by a smooth function. So spectral measure is like a characteristic function, so I'm approximating characteristic function by a smooth function, that's all. And then we observe this difference to evaluate the characteristic, that smoothened characteristic function at h0 and h0 plus sv, and you can see, you can write it as a double integral like this. And here you have a slight trick. You multiply by alpha minus beta and divide by alpha minus beta, and the numerator you can rewrite it as if you have inserted a v here. In other words, if you think of v as h0 plus sv minus h0 divided by s, then the spectral family will have the effect of producing alpha minus beta, which will cancel this, that's all. Now, this, look at this. This gives you this spectral measure. Think of this as E0 d alpha multiplication on the left, Es d beta as a multiplication on the right of a Hilbert-Schmidt element. That is what I have written here. This leads to a spectral measure on the plane. So this extends to a spectral measure B2H valued, that is Hilbert-Schmidt operator valued spectral measure on the plane with total variation less than or equal to 1. So you use that. So now we want to compute this trace, and you get this formula where G delta alpha cross delta beta, that is the measure on the plane, is acting on this Hilbert-Schmidt operator and this is the inner product in the Hilbert-Schmidt space, which is same as the trace given there. So this you read off as non-negative because this is negative. It is a decreasing function. But this minus sign with the decreasing property gives me positivity, and we read off this to be non-negative for all lambda and epsilon. And now we take the limit, well, this is sins, not science. As epsilon goes to 0, this is the approximate characteristic function. This is similarly, they converge strongly to their respective spectral measures, and our spectral family is right continuous, and this is definition, not definition. It follows that this is non-negative, and therefore if we go back a couple of slides here, this is non-negative, that is what we have just proved, and therefore eta is non-negative. So that proves the non-negativity of eta as claimed. Therefore eta is non-negative. Now the L1 norm of eta or the integral you can easily calculate because you just put the quadratic polynomial here, then this is exactly identity, and therefore from the left hand side you calculate what has been asserted. Now comes the, so this we have proven the Koplienko type formula for finite dimension. The next step is to approximate infinite problems to finite dimensional problems. And this is the, as I said, Weil von Neumann type of construction. It is an adaptation from Weil von Neumann's proof for something else that did that. So A, let be a self-adjoint operator in an infinite dimensional space, Hilbert space. Let this be a set of normalized vectors. Then we can find a finite rank projection P such that all these approximations takes place. For a given epsilon, I can P is close to 1 in this sense and also in these senses. So this 1 minus P AP, the off-diagonal part with respect to P of the operator A, is Hilbert-Schmidt, and it is small in Hilbert-Schmidt norm. So this off-diagonal part of A as well as the group generated by A is small, uniformly in T in compact. Just a comment, Weil and von Neumann tried to prove, use these results or try to construct this kind of thing. They had a different aim. Weil first proved that I give you a self-adjoint operator with any spectrum, that is, let's say completely only continuous spectrum. Then he showed I can find a self-adjoint Hilbert-Schmidt operator of arbitrarily small norm, that is less than epsilon, such that A plus B has only eigenvalues. That was the aim. Okay. Von Neumann extended it for unbounded self-adjoint operator. That's why this theorem is called Weil von Neumann theorem. So I can, whatever spectrum you have, I can add a very small perturbation and make the whole problem eigenvalue problem. Of course, they may not be isolated. Nowhere you are asserting that your eigenvalues are isolated. It can be everywhere dense, for example. That can happen, all the rationals and so on. But we have adapted that theorem to our end, and that is what we used in our earlier paper as well. So in our problem now, we look at it this way. So H and H naught as before. V is the perturbation which is Hilbert-Schmidt by hypothesis. Then there exists this projection P of finite rank. Given an epsilon, I can find this such that. So this projection depends on two things, epsilon of course and V and H naught. So it depends on all the parameters of the problem such that, as I said, the off-diagonal elements of H naught and H are small in Hilbert-Schmidt norm. So the proof is not important. Let me just get over them. Now this is a remark. So we can restate the problem as I get a sequence of finite rank projections such that these off-diagonal things happen of H naught and H. But we cannot conclude that Pn converges to identity. They are not equivalent statements. We are not asserting that Pn is a sequence of finite rank projections which are converging to identity, because it depends too much on this given operator. Okay. So now we use this lemma to prove our theorem. First is the reduction of the to finite dimension. As I had asserted, that if H and H naught are two bounded self-adjoint operators such that the difference is Hilbert-Schmidt, then there exists a sequence of finite rank projections using the previous theorem such that the required trace, here is the first order derivative frechet subtracted, is obtained as a limit of same formula in that finite dimensional compression. That's all this statement says, where small p is a polynomial. Well, this is a little bit of computation. I won't again go through that. So the final statement is the Koplienko formula for bounded operators. Well, this is a standard statement. Two bounded self-adjoint operators such that the difference is Hilbert-Schmidt. Then there exists a unique non-negative L1 function supported in that interval, which is the union of the spectral interval for H and H naught, such that the trace formula, as I had asserted, is valid. And furthermore, that integral expression for eta also is valid. So proof is trivial once you have the previous theorem, because we have proven it for finite dimension and we have proven it for the approximation formula. Therefore, this is limit of the approximation, and therefore it is, and for this I have proven the Koplienko formula for finite dimension. So I get an eta n given that way. So all I have to now prove that eta n converges in a suitable way. Now for that, you see in the earlier Crane's formula case, we used entirely different philosophy. There the function here that appeared here was bounded, in fact plus minus one valued function. Here it is not like that. This is not necessarily a bounded function, but it is an L1 function, that we know. For each n it is an L1 function. So we can hope for an L1 convergence. So that is what we are aiming to prove. That is the next part, that all we are going to prove is that this sequence is L1 Cauchy. To prove L1 Cauchy, we look at it, use the weak star convergence uniform with respect to L infinity. So you take an L infinity function and form this integral, and we want to show that the convergence is uniform with respect to the L infinity norm of f. And that will prove that eta n converges to something called eta in L1. Well, I have not proven it here, but that is what we do. That is what we prove we get an explicit expression for these, as you can see. This, I can use this expression, so I get these expressions for n and m, and then I'll have to estimate the difference in trace norm, uniform in L infinity norm of f, such that this goes to 0. That's the last step that we do. Now, we want to extend it to unbounded operator. Now, only difference from bounded to unbounded essentially is the support of the spectrum. The spectral support can become the whole real line in the case of unbounded self-adjoint operator. Therefore, polynomial is not a good object to deal with. Instead, the exponential function is a better object to deal with. And therefore, naturally, Fourier transform theory is lurking in the background. So what do we do? So the lemma is appropriately stated. Instead of polynomials, you see these e to the power it's all over. So there exists a sequence Pn just as before, such that this difference, which is what we want to compute, is approximable by the difference of the same thing in the finite dimensional compression. Again, the proof I will skip. Now this is the H and H of a two self-adjoint operator in infinite dimensional space. There exists a non-unique L1 function such that this is true. This is for the exponential function that I am asserting this theorem. So just few steps. So reduce the problem to finite dimensional problem, as I have been saying all along. Therefore, I get an eta n which gives me this formula in finite dimension. That is the right hand side here is given by this, so I have to take a limit of this. Existence for eta follows by a similar method as earlier, except that one has to pay attention now that my interval is infinite. So the indefinite integral of f and g, etc., that we have used in the earlier theorem are possibly unbounded operators. Okay, so we cannot be so, we have to be a little bit more careful. So the statement of the theorem is as follows. So in order to avoid that problem, we restrict the class of functions to Schwarz class of functions. So I look at the Schwarz class of functions, smooth functions of rapid decrease on the real line, and then this difference, which is our object of interest, is shown first to be trace class, and the trace is exactly what you expect. So we have proven this result for nice functions. By that I mean here this, where eta is this non-negative L1 function. So we proved the limit of those eta n's in the earlier slide, and then proved the formula for Schwarz class function, the trace formula. Now this can be extended, so the next remark essentially says this formula can be extended to a more general class. For example, this class, in fact this is probably the largest class, that phi could have a linear part, and otherwise it would have to be this transform of a complex measure nu on the real line. Now, of course, this function may make sense, but the operator out of it may not make sense. So that there has to be a caution, because if you put a self-adjoint operator here and form the functional calculus, that will be an unbounded self-adjoint operator, which will be more like the square of the operator rather than the operator itself. Now, the two operators relatively can be controlled, but the square of each may not be controlled with respect to the other. Okay? And by that I mean h and h naught difference is Hilbert-Schmidt, so it is pretty nice. But h square and h naught square difference is not going to be Hilbert-Schmidt. That is clear. And in fact, the domains will be pretty pathological relative to each other. So in general, if you form a function like this, as a function it will make a reasonable sense, no problem. But when you form the operator, you may not find a good domain on which this operator will make sense as an operator. So one has to be a little more cautious in stating, oh, this is what I want to go to next. So one has to interpret the left-hand side appropriately. Okay. This function may be h square, for example. This may be h naught square, and if h square and h naught square do not have a domain where they are well defined together, that is, intersection is too small, then you do not have a good operator. Okay? That can happen. So this, what it says, that provided this function may make, this formula will make sense provided the left-hand side makes sense as an operator. That's a separate problem. Okay, so I have a little more time. Jacob, I have a little time, right?
Yes.
Okay. Okay, so next is the next order trace formula. So one can ask this question again. The problem becomes more and more complicated, of course. So this is the more recent result that we have got, namely third order trace formula. That is, you can see here, this is for bounded operators. A is self-adjoint. V is, you see here, B2. We are able to prove this formula only for B2, though you would normally expect that you should be able to extend this to B3, the next Saturn class. But so far, there no proof exists for B3. So the statement is, then there exists a unique real-valued function, not necessarily positive anymore, such that trace of, you see, I'm now subtracting the second order Fresher derivative of the function, D2, evaluated as a quadratic form on VV, bilinear form VV, is given by the third derivative times this spectral function eta, where P as before is a polynomial, and sort of expected that integral of eta is 1/6, 1 by 3, 3 factorial actually is trace V cube. That's why I said the more natural hypothesis for this theorem would be V in B3, but that is not possible to prove so far. So this is, and for the unbounded case also we have a similar statement. Okay. Sketch of the proof. So again we have to compute. This one we had already computed earlier, but this one you have to compute. It is not a very difficult computation, and you do that and you form this expression, which is our basic expression for the third order, trace of the perturbed function minus the unperturbed function minus the first derivative minus half the second derivative. So this is the mean value theorem, I mean the Taylor expansion up to the second order here on the left hand side. And that is given as this. Notice there is this, now previously I had a single integral, now I have a double iterated integral. Okay. And there is this a tau is a plus tau v, like I had been saying earlier. I called it s earlier, but I have now double integral, that's why a plus tau v. And here is the perturbation v appears twice. So in fact, it is worth speculating if I had written up to the pth order here, what would be the formula here? Okay. We have not found, there is a combinatorial problem. I think there will be more summations, but it should not be difficult to figure out what should be the appropriate formula on the right hand side if I go to arbitrary order. So that's the main formula that you work with. If I derive this formula, well, under trace, the fundamental theorem of integral calculus works for Fresher differentiable map. And the following facts we use to get this, wait a minute. We also use the fact, given a self-adjoint bounded operator A and an X in Hilbert-Schmidt class, I can break the Hilbert-Schmidt operator class into a direct sum of x1 and x2. That is, x I can break up into x1 and x2 with respect to the natural inner product in B2H under trace, where each of the x1 and x2 can be chosen to be self-adjoint if x is. So it is x and A and x are both self-adjoint here. Moreover, if I take A tau instead of A and make this decomposition with respect to A tau, then each of these components, x j tau, j1 1 and 2, as a map from tau to xj tau, taking values in B2H, is a continuous map. Also, the philosophy here is very similar to the proof of Koplienko formula, namely eta is obtained as a uniform W star limit of a sequence eta n which has explicit expression. Now, to handle the case A unbounded, here we need a little bit of restriction. We are able to prove so far with a slight restriction, namely spectrum of A is bounded below. That means it doesn't go to minus infinity. So it is above some point. So we have this following theorem. So A is an unbounded self-adjoint operator. Sigma A is from B to infinity. B is the lower bound of the spectrum. And B is a self-adjoint operator, which is Hilbert-Schmidt. Then there exists a unique real-valued function eta. Notice the class L1 of R with this measure, which is absolutely continuous with respect to Lebesgue, but not Lebesgue itself, for some epsilon positive, such that for every Schwartz function, the second order difference or third order difference is given by the triple prime of the function times this eta. Okay. Now this is new because I think Dykema and Skripka also announced such a result, but they got a measure only. They showed that there exists a measure here, which is not, I mean, there was no claim at absolute continuity, but we have absolute continuity, that there is a spectral function. So as usual, I mean, the question rises, can one derive a general formula? And Dykema and Skripka does have an approach to the general formula, which, as I said, they use inverse Cauchy transform, being expert in that area, and it is really quite complicated. It is far removed from the method that I have used. Well, that's all I have to say, and these are some of the references. There is the Dykema and Skripka's main paper, and these are the older papers of the Russian school. And this is the old paper of Koplienko, where he announced this result, which, as I said, unfortunately proof is wrong. This is Crane's old, no, this is not the original paper. This is a paper reprinted or republished in a later publication edited by Goberg. This is a result announced by these authors. They have worked extensively in this area, this group, Sukhochev and Potapov from Australia. And this is our papers, and thank you.